Okay, back again, and we're going to continue with our little Cmos introduction with the 4049. And I forgot to mention that other chips also work. In particular, you could use the 4069 if you happen to have one. You're going to have to look up. I'm going to show you a picture of the thing, and then you can pause the video. So that's how the 4069 is set up. So it might be slightly different. I should play around with the 4069 and see how the characteristics differ, because this actually does kind of rely a little bit on the particulars of these ICs. And another one you could also use, I think it's the 74HC14, or it might be 04, one of those two. That's a different series, but it's a Cmos chip as well. And you could use one that's not. You could use like the 74LS something or other, and that's a TTL one. But I don't know if it will work exactly the same. So we're going to play with TTL at some point so that I learn how the characteristics of them as well. So anyway, back to this. So this is the circuit we came up with, and here is it here. And this one kind of works. So this is where we were up to, and it sort of works, and I said this is not the best way of doing it, and that we want to get it a little bit better like I've done here. And I've got some extra resistors in here. So, but the first thing I want to talk about is just going to go over some things about the ICs. So, looking back at our little picture, I should actually put a little sticker on the page, but if I do this enough, hopefully, I'm going to turn that off just in case it breaks. Hopefully, it will just be like always open on this page here. So the trick with Cmos things is that on an input, you want to have, the ideal thing is to have a very high input resistance, and on an output to have a very low output resistance. And this is because you want the output to, well, the best way of explaining it, but just say for now, in a later video I have a better way of explaining it. It's too late at night to think of this, but definitely for the input, you can understand why. Well, you want it to be a low output resistance so that it can actually power other things and do more interesting things. But you want it to be an input. If it's a high input resistance, then basically you can sense the voltage without actually affecting much. And in this case here, in Cmos things, this is the really cool thing about them, is that the input, well, in this case we'll say the input impedance, which is like a more general term for resistance, and includes, it includes other things than just resistance. So the more general term is impedance. And so these are high impedance things when you go into the inputs. And they're so high impedance that they barely take any electricity at all, or electric current at all goes into them. They have it's essentially like in the millions and billions of ohms or something like that. So it's something ridiculously high. And this is kind of important. But also the major problem with this is that the output resistance is quite low. So it's effectively quite low. So we'll have to look into what's actually happening at the output one day. But today we're not going to. But you can just imagine that it has an effectively low resistance. So why that causes a problem and why this little circuit doesn't work is, here is my little picture of this. So this is a gate. We'll call these little digital circuity things are called gates. So there's quite a few different types, but this is the inverting gate, and this is like the simplest one that has one input and one output. Some of them have two inputs and some of them have more than two inputs. But in this case here we have our inverse gate, or a NOT gate if you do like Boolean stuff, which we will be doing because that's what this all is. But that's not that important. So when I have this little red thing here, this little square is meant to be the internal resistance, or the resistance of the gate itself. The output resistance is the red one here, and this is coming out of the IC at this point here. So that pen doesn't even work. I'll use this one. That's the output. That's the pin itself. So this is where it comes out into the real world, and then we've got our little looking at our circuit. Our resistor and our LED in the opposite way around, but it doesn't matter, these can be swapped around. So we've got our resistor and our LED coming out of here. And if you're looking at this, you might go, ooh, this is suspiciously like a voltage divider. So when you have these two little resistors, and then you're measuring the voltage in the middle here. So on my original diagram, oh, it's right underneath this one. Back here, we've got this situation. So what I'm saying here is I'm saying there's actually a resistor about there. And this wire is going back and coming around here, and over here we have another resistor. So it looks like this. So this is essentially a voltage divider, and this is where things get tricky. So if this is quite low, and it's probably, I don't know, I'm guessing about 100 or something, I don't know, some quite low, 100 ohms, let's just say it's 100 ohms. And this one here, in my example, in my first example, when I use the big one here, this is 100 ohms too. And so this is kind of important. So this thing here is using up 2.5. Actually, it's more than it's less than 100 ohms. We can actually kind of test it. I'll bring this guy back again, and I'll show you what I mean. So we can assume, let's just say this is 50 ohms. So I'm going to draw it. Sorry, it's going to be upside down. That's 50 ohms. Alright, so I'm going to do it side on, and this is about 100 ohms. And we're going to say this is actually 3 volts. So what's coming out of this point here is about 5 volts, because it's 5 volts going into the power thing, and this thing's using up about 2 volts. So we've gone through another, sorry, it's all upside down. 2 volts. I knew there was going to be a problem. It's 5 volts, it's upside down, just deal with it, it's life. Alright, and so what we have here is 3 volts. So this is 100 volts. Maybe it should be higher, because I know it actually comes out when you do this. It's about 2.5 actually is the voltage after you've divided it up like this. So I don't really know. We could kind of work it out. Except I have to do it the other way. Since I haven't done it before and I refuse to do this normal way videos, it's not going to work. But I'm going to do it like this way. Alright, so we have 3 volts going across it. Alright, what do I want to do? Oh, I can't remember. I can't think about it. You can do it as an exercise for the reader. But it does have an internal resistance, and it has this resistor. And so this divides up the voltage. So you come out here and you've got 3 volts. So this one here is using up 3. So in this case here, we'll just do an example with this one. 100 here and 50 here. So you're going to end up with 2 volts across that one, and you're going to end up with 1 volt across that one, because that is, if you add them up, it's 150. That is 2/3 of 150. That is 1/3 of 150. So the voltage being used up over this is going to be 1/3 of what we've got, which is, so we've got 3 volts because we used up 2 volts for the LED. And then we've got that. So in this case here, you'd get 4 volts. So that would be, so if we were to read the voltage here, 2 plus 2 is 4, right, which is probably enough to register as a high voltage, right? But let's just say we had 10 over here. Alright, is that what I want? No, I want to go the other way. So let's just make it 100 over here. So this is 100 ohms, the internal one, and that's 100 ohms. So we've got 3 volts. And half's going here and half's going here. So this is actually going to end up being 1.5 volts. And so we've dropped that, and so if you were to read this, you would be reading 3.5 volts. And again, if you went up to say 200, then it would be the other way around. And so 1 volt is going to be over here, 2 volts is going to get used up here, and this one, this is going to be a terrible video, just trust me on this, is going to go down to about 3 volts. I hope I've done that correctly. And as you keep going, so whatever the voltage is, it must actually be quite a bit higher than this. So I'll show you what I mean. Let's just take out this little circuit, activate it, and we're going to read, but I have to actually, we kind of know what it is from this, because it works with the 300 ohms and it doesn't work with the 100 ohms. So if we put the 100 ohm in there instead, hopefully we can get the light to come on. This is not going to work. Oh, this is not the way that I did it. sorry, I know how I did this before. So working out the actual correct place to measure things is always a tricky bit. So I'm just going to plonk a wire in there. So this is my ground reference, and that's going to go to there. So because the light's out at the moment, alright, that means the output pin, the output, I'm going to look at this picture, now it's upside down. That's great. Okay. Now I'm going to read this thing. So, looking at this, alright, this pin here, so pin number 2 is the output from inverter 3, so that's probably high at the moment. So bringing this over here, this is a very complicated way of doing things. So I've got my ground attached to here, and then I'm going to measure the voltage coming out of pin 2. Can you actually see that on the camera? You can't because there's wires everywhere. Let's activate the light. Alright, I think the other one was much easier to read. I should be using the other multimeter. And it's not going to show anything. Oops. Okay, don't go touching that one. That one says 5 volts coming out of that pin. And I've gone and turned it off. Come back on. So, what is it going to do? Oh, well, that's rotten. Well, it worked before. I'm going to come up with a better example next time. But anyway, what happens is because this one is quite low, so when the resistance on the output is too low, then the voltage that you read off here, so most of the voltage, you know, the cost, and you know, if you look at it like you have to spend most of your voltage on the internal resistance, it's still going to have, you know, it's going to have a low current, but most of it's going to be spent on the internal resistance, and it's going to go through here. But the voltage it's going to be reading on the other end is going to be too low to register as a high. So even though you've got high coming out of here, so say 5 volts coming out of here, it's going to be registered as a low once you get round to the other side, because you're actually measuring it from this point and not from that point. Because that's an ideal point, but this is the reality of things. And also these are inside the here there's transistors, so when we talk about transistors we'll see why this might come out as a way of explaining it. But anyway, so that's the kind of the problem. So it will work if you have a high enough resistance. So I did fix this before by putting in, so often you see when they do these things they have a 1K, a 1000 ohm resistance for the output. Because these things aren't really designed to power LEDs in the first place, and so that's the problem. And so they usually, if you have a high enough resistance, though it isn't. So if you have a high enough resistance, then most of the voltage will be used over that resistor, and then when you read it, it will still be pretty high. So if I remember before, also that's the neat thing about the inputs having really high resistance, is that it doesn't really matter. You'll be able to. We will see what I mean. We're going to come to that in a second. So just ignore what I just said. So the two solutions to fix this little problem is to use have a high resistance load for the output, or use another output of the inverter to buffer it, and that's exactly what I actually do over here. So there's actually 3 used. I'm just running, and here's my picture of it. So we're going to get here. So this is the picture of what we're getting to. So in here I've got what I had before, and I've put in some extra resistors, and we're going to talk about that in a second. So that's the other issue that we're going to look at. But the last thing is, in this case here, I put in another one of these. So this is buffering it. So the resistance going into here is super high. It's like, you know, billions, right? Billions of ohms. And so it doesn't really matter what the internal resistance is here. Most of it's gonna still end up always being a 5 volt output here, or close to 5 volts on the output. So it's always going to be high no matter what the internal resistance was, because the output load is a very high resistance, high impedance thing. And then of course once you've got the output, then you can use that for whatever you want and turn the LED on. So in this case that's exactly what I've done here. So even though I pulled out the resistor, which is a bit silly, I think it went somewhere. It went like, we'll just say it went like that, and it'll be fine. So even though I've only got 100 ohms here, it works fine because I'm buffering it via one of these things here. The only problem, of course, is now it works the opposite way around because this has inverted it, which sometimes is fine. You can just put it into your circuit and just say, well, this is the actual output. So instead of saying this button turns it on, this button turns it on, and this button turns it off. But of course you could put another one on, and then you've gone and got back to what you wanted. So if you have two inverters, you get back to the original state. And of course there is a chip, the 4050, which just buffers things without inverting it, so a non-inverting buffer. But that's the first part, and I hope that kind of made a little bit of sense as to why it doesn't work that way. And of course that's why the light is dim when you turn this on. It's dimmer than it could be. So when I hold the button down, it's brighter than when I let go. And it's bright because when I press the button down, I've got 5 volts coming through here, going straight into, that's not the one I want. So many pictures. So I've got, oh my goodness. Like, why don't you use the slideshow thing? So in this case, I've got 5 volts going straight into there. So it's going to be getting 5 volts from there. So it's going to be full brightness. But when I let go, it's only coming out of here, and then there's the resistance going into it. So it won't be as bright. So that's why you have the inconsistency. And so my final model, anyhow, is this one here, where you have these two resistors. And the reason I felt like doing this, and it goes back to the low output resistance. Though if you can see, I was kind of indicating that I think the internal resistance is going to be a couple of hundred ohms, which means you probably don't even need a resistor to do the LED. But having said that, if there's a resistance inside of this, then of course it's going to generate heat, and it might not be able to cope with much power going through it. We haven't talked about power at all yet. Just the quick preview: power is the voltage times the current, and that's going to be used up as heat. And so the internal resistance may not be able to cope with too much heat. So plugging a resistor straight on might not be a good idea. Though I did see in the book that I had that yes, you can do that for some things. Just put the LED straight on without a resistor for low enough voltages. So that might work. We can try that. That seems to work fine with 4017s, which we're going to look at a later date. But anyway, the problem is with this is that there's a low output resistance. So in my original drawing, back to here, without this, let's just say I pressed this button and it's 5 volts. So if it was 5 volts and it goes in there, and then you go through here, and this is inverted and that goes back down, I think in this case here the problem isn't too bad. But let's just say that this was outputting low, so this was a low voltage, and this was 5 volts going here. So when it's low, it's sinking current, and so it's allowing current to flow into it, and when it's high, it's sourcing current, it's letting current flow out of it. And by that I mean conventional current, which is the opposite way around to what electrons do. But it doesn't actually matter, so don't worry about that. It just stick to one way, and it makes sense. But in this case, you're saying that 5 volts is going into here if this was low. So what I mean is if I press the button, not only is the 5 volts going here, but remember, this is super high resistance, and so no actual current's really flowing into here. So essentially no current flows into the input, but all the current's going to go into here. And if it's got a reasonably low resistance, you've got 5 volts going straight into there, and that could damage it, right? Because as I just said, it may have a couple of hundred ohms of resistance. But that's all going to get converted into heat inside the IC, and that could damage it. Now in the case of this thing, I don't think it doesn't matter too much, because as soon as I press the 5 volt button, yes, it's going to go straight into there, but then it's going to convert this. So this is going to go high here, this is going to go low, come around here, this is going to go low into here, but it's going to turn this to high, so this will be 5 volts. So the voltage difference between these two things is going to suddenly become very, very small. So this will be 5 volts and this will be 5 volts. So the current won't be flowing into there. So it's only going to flow into there for a small instance. It's not going to flow there for a long time. But if you were to hold down, so the other problem is, maybe you hold this, so the same thing happens over here, right? If you push this button down, then the current's going to go into here as well. And now some of it's a bit better off with this one, right? Because it's going to get split up and it's going to go into the LED. But as I said, this has a low resistance. And if you're buffering it, it's going to be the same problem. So it's still going to go in there, but only for a brief second. But what if you were to hold both buttons down at the same time, because you can't trust the person using it? So then it's going to be continually oscillating between these two things. So it's going to cause bad problems. So my ultimate solution was to put some resistors in here. That's not my ultimate solution. That's my second ultimate solution, which I haven't tried yet, and I don't think we're going to have time to. So here I have a resistor between the button going into here. And this doesn't change the voltage going into here. This is still 5 volts, but there's a big resistor in the way, and so it doesn't cause much current to actually flow into here either. So in my other model, this one here, I think there's something like 33,000 or whatever. They could be quite high. Like it could be really, really high, and it's not actually going to affect this thing here. So the other thing to think about is, well, okay, I put a resistor in the way for the 5 volts to go into this, to not go into the output of this. But what about the output of this going into here? Well, if I suddenly put a big resistor in the way, aren't I going to stop this from happening? So if this is high, or this is high, and there's a big resistor in the way, then maybe you might imagine, if you don't know what you're doing, that this will be quite low, that you're going to use up all your voltage going through here, and then it's going to be 0 volts down here, or it's going to be a low value here. So even though it's high here, it's going to end up being low here because you've got this giant resistor in the way. But the important thing to remember is this has a very, very high impedance. So it's super, super high. So it's way, way higher than 33,000 or 100,000, or maybe even 1,000,000 ohms is not going to be enough big problem here, because this is like 1,000,000,000 ohms. So if you divide this up as a voltage divider, and I have a huge thing here and a relatively tiny thing here, then most of the voltage is going to go into here, and so it's still, I think, going to have very little current is going to flow through here. And so you're still going to get 5 volts coming through here, or a high voltage over here, even though this is a big resistance. As long as it's nowhere near this, the resistance of the input, you won't have a problem. And so it doesn't really matter too much that this is a high resistance for this point, but it does matter. So it doesn't matter going that way, but it does matter going that way. So I hope that makes sense. And so there's another one over here for exactly the same reason. So that one's going a high resistance there. This is just to go into here, so the 5 volts goes into there, and it doesn't really go that way back into here, so it's not going to affect the output in any way. It's not going to affect the input of this, and so this thing isn't going to be sucking up current and creating heat. So I hope that made sense. I don't know if it does. But the other way of doing it, I thought, and I was going to try it, but we've run out of time, is to do a similar thing. So if you don't want to provide, so you have 2 buttons here, but in this case the buttons are now between the output of this one and the input of this one. So in the previous one, the button was over here, and this button is connected to the input of this, and this button is connected to the input of this. In this case here, they're both effectively connected to the input of this, but this one is pulling it low, and that one is pulling it high. And the resistor, there's 2 resistors here, so you don't get away from having 2 resistors, but it's important in this case here to have 2 resistors, to have a resistor between these 2, because what if you've got a silly user of your device and they decide to hold both buttons down, then the plus voltage is going to go straight through here, and if there wasn't anything there, it would just be a short circuit. So, and because of going through what I've just said about the resistances and dividing the voltage division, and the fact that this has a very high impedance, then these things don't really matter. So you're still going to get a low voltage going in there if you hold that button down, and you're still going to get a high voltage going into there, obviously, because it's connected directly up regardless. So hopefully that kind of makes sense if you wanted to try that, but we've run out of time, so we won't try that today. And I think that was pretty much it. So I hope that all made sense. And yes, so this doesn't work that well, but this method works a lot better, is the moral of the story. So I just checked that this actually still works. And this one's broken. Oh, what did I do wrong? Oh. Actually, oh, that was supposed to come out of there. Alright. So, yes. So this one here is connected to yet another one, and that's the way I think it should work. If I had like a thing to measure the temperature, we could actually see on the two different models if this one actually is heating up more than this one. Well, this one should not be heating up, because all the heat's going to end up in the resistors anyhow. So the resistors will be warming up a bit, like very microscopically. But if you're like a little tiny IC, then you know microscopic changes and things are bad. So what's fine for this is not going to be fine for what's inside of here, because it's very small. So cool. Thanks for watching. Like, share, subscribe, and keep turning your lights on and off, on and off. Just don't stop pressing those buttons. And next time we're going to do this. We're going to do similar things, but this is, well, we'll do this again. We'll come back to this later on with a different kind of chip called a 4011. So thanks for watching. Bye. Like, share, and subscribe.